So far this week we've talked about solving linear systems ax equals b, where a is typically square but doesn't have any other special properties. It turns out that if matrices do have special properties, for example they are symmetric, or better yet they're symmetric positive definite, or extending that Hermitian positive definite, then there are algorithms that reduce the number of operations required to perform the factorization, and that then means that you can get your answer faster. So to motivate all of this and what these special properties are, let's have a look at something that you should be familiar with. Y equals alpha x squared, where y and x and alpha are all scalars. Wait a minute, we don't like using Roman letters for scalars, so we really should have written this as psi is equal to alpha times chi squared. Okay? And for now, let's just say that these are all real valued numbers. Well, we could think of this instead as chi alpha times chi, and we could also think of this as chi transpose alpha chi, and if chi is real valued, then we could even say this is equal to chi Hermitian transpose alpha times chi. Now, what did you learn about this special case? Well, you learned that if alpha is positive, then this quadratic equation is concave up and therefore has a minimum. And if alpha is negative, then it's concave down and it has a maximum. In other words, this actually looks something like this. And in particular, chi not equal to 0 implies that psi, which of course is equal to chi Hermitian alpha chi, is greater than 0. Okay, well, what is the generalization of that? If you're given a matrix A, then you can look at psi is equal to x Hermitian A times x. This obviously is a scalar, right? Now, if A is symmetric and positive definite, let's take the case where x only has 2 entries and therefore A is 2 by 2. If you have the situation where x not being this 0 vector automatically implies that x Hermitian ax is greater than 0, then the way to visualize this is that this now becomes a 2-dimensional plane, and your function is now concave up. You have a paraboloid that extends up. Okay? And obviously you can extend that idea to higher dimensions yet, although it's a little hard to visualize that. The important thing is it has a minimum. Okay? And the minimum obviously is at the vector x equals 0. Okay? So it turns out that if a matrix has this property, and this property here is known as being Hermitian positive definite, and the real valued equivalent to that is symmetric positive definite, A has to be Hermitian, or symmetric in the real valued case, and then x not being 0 has to imply that x Hermitian ax is greater than 0. Now, if A is not Hermitian, then we say that it is merely positive definite. And you can have negative definite, you can have negative negative indefinite, which means that it actually could be equal to 0, but those are all special cases that you can go look up when you actually need them. So, it turns out that if a matrix is Hermitian positive definite, then we can create a variant on LU factorization known as Cholesky factorization that can take advantage of the symmetry of the Hermitian nature of matrix A.